Hello everyone. Today we are going to look at how SIS disease model can be modeled. In SIS, S means susceptibles and I means infected. These are compartmental type of disease models in which population are divided into various compartments. Here the two compartments are S for susceptibles and I for infected people. So basically the equation corresponding to SIR model, I will explain that later. First of all, this is the main dynamics of SIS model. So the susceptible people move to infectious compartment with a rate beta, that is the infectious rate, as well as the infectious people move back to susceptible compartment with a rate gamma. So these are the two rates associated with SIS disease model, and so we are going to model this. The differential equation corresponding to beta and gamma are susceptibles and infected are minus beta times S into I divided by N plus gamma I. That means that beta times S minus S times I divided by N, and S plus I is actually N. So this much amount of people move from susceptible compartment to the infected compartment. That is why we have put the minus sign here, and the corresponding term is added here also. Similarly, gamma times I, the gamma means the recovery rate, gamma times the total population of infected people are going to the susceptible part again. That means there is no permanent immunity. No permanent immunity like the common fever, the common cold, like that thing. Those disease which doesn't have permanent immunity will keep on arriving again and again to the same person. So the two equations are ds is equal to minus beta si by n plus gamma I, and di is equal to beta I s by n minus gamma I. So now let's model this with the function. So the parameters are the time we should add, the initial number of susceptibles as well as infected people should be initialized, and the parameters means beta as well as gamma should be initialized here. And we initialized the two differential equations as difference equations here, means since we considering each process happens in unit time, or dt is equal to 1. So this is the way how deSolve can be used to solve differential equations. And now let's put various values for this model. So let the parameters are beta is equal to 0.5 and gamma is equal to 0.2, and the initial number of susceptibles were 100, and initial number of infected people is 1, and the time is calculating from 0 to 100 with an increment of 1. So this is our deSolve function, ODE. We implemented the name of the function, and the parameters are initialized here, that is the state, the parameters and the time are initialized here, and we are returning it as a data frame, naming it as out. Before that, let me check some. Okay, I will name it as dx and dy itself. Here ds and di. Okay, that was the error. Also they are showing some problem with this. Oh, here I should add the s. Okay, now you can see. So I have plotted this. The x-axis is time and y-axis is the population of susceptible as well as infected people. The black line indicate the number of susceptibles over time, and the red line indicate number of infected people over time, which means that there is a constant value. They both converge to a constant value, which means that there is always a fraction of people who are infected in the population, as well as there is always a particular fraction of susceptibles in that population. So such disease always persist in population, that will not go easily. That is actually because of the lack of permanent immunity, as we have discussed here. But in the case of a permanent immunity, like chickenpox or smallpox, we should consider the recovered fraction also along with this equation, and all the infected people go to the recovered fraction so that they won't be susceptible again. So this is the main difference between SIS model and SIR model. The recovered people going again to the infected, the susceptible part. Thank you.